Magnetism has been a topic for discussion since the early days of the radiologic profession. When one discusses the function of an X-ray tube, the acceleration of electrons across the tube involves magnetic-like forces. With the advent of MR imaging in the early 1980s, an understanding of magnets and magnetic fields has become even more important in the field of medical imaging. In its simplest form, magnetism is defined as the ability of a material or device to attract ferrous metals. While this definition works to define magnetic fields, it doesn't cover all things that magnetic fields can affect. For example, the hydrogen protons in your body can be uniformly affected if the magnetic field is strong enough, as in an MR scanner. Additionally, free charged subatomic particles like protons or electrons can be affected by magnetic fields. Electromagnets are also used to steer or focus electron beams, as in therapy applications. On the periodic chart, there are 3 ferrous metals. A ferrous metal is literally defined as an iron-like material. It is unclear exactly what makes a metal ferrous. It is thought the electron configuration, which not only includes the electron orbitals, but also the orientation and proportion of outer electron spin. It is spinning of the electrons in the atom that create the magnetic field. Whenever electrons move or spin, a magnetic field has been found around the electron. If one inspects a ferrous metal on the atomic level, you'll find small particles that exhibit magnetic properties. These magnetic particles are called magnetic domains, and they are unique to ferrous metals. There are 3 ferrous metals, and they are iron. Iron is the first ferrous metal. The Latin word for iron is ferrum, which explains why Fe is used for its chemical symbol. Move one position up on the periodic chart, and we find that cobalt is the second ferrous metal. Move one more slot up on the periodic chart, and we find nickel, the third ferrous metal. If we look inside a non-magnetized ferrous metal, we'll find a number of grains or crystals that are acting as small magnets. These small magnets are called magnetic domains. In most metals, the domains are randomly arranged, and the force of a left-to-right domain will cancel the force of a domain that is oriented right to left. In this material, the random arrangement of domains are oriented in such a way that their collective force is 0. In a magnetized ferrous metal, the domains are aligned and work together. The more domains that are aligned, the stronger the magnet will be. Magnets can possess a range of strengths from weak attraction to strong attraction, depending upon the number of domains that are aligned and working together. In today's world, there are some metals that can be made into a magnet. Additionally, there are magnets that can be energized and de-energized with the flip of the switch. One of the older forms of alloy-based magnets is the Alnico magnet. Alnico magnets consist of an alloy of aluminum, nickel, and cobalt. Alnico magnets are stronger than iron magnets and are used when their additional strength is important. Neodymium iron boron magnets make some of the strongest permanent magnets available in today's world. The important characteristic of an electromagnet is that it can be turned on or off using a switch. The push-button locks that secure position of your X-ray tube during an exam are electromagnets. MR scanners are electromagnets with a difference. The electrical current is introduced in the coils, and it circulates endlessly in the coils because they are supercooled with liquid helium to the point where resistance in the coil is near 0. The MR department needs a super strong electromagnet that can be turned off for delivery, but once installed, be energized. Once activated, the MR electromagnet cannot be turned off without incurring great expense by quickly dumping the liquid helium. Electromagnets begin as a coil of conductive wire, and the coil is connected to a power source like a battery. Connecting a battery to a coil of wire is the source of moving electrons, and moving electrons create magnetic field around the wire. Often a bar or core of ferrous metal is added inside the coil to concentrate and magnify the magnetic field. If one sprinkles iron filings around a magnet, they will align themselves in a circular pattern. This pattern is known as the magnet's lines of force. Magnets can affect ferrous metal without touching it. The lines of force align themselves in a circular pattern outside the magnet. The concentration of lines of force indicate a magnet's strength. A magnet with few lines of force will be weak or mildly magnetic. A magnet with many lines of force indicates a stronger magnet. The magnetic lines of force are designated to flow from the north and re-enter the magnet at the south pole. An important rule of magnets is that like poles repel and unlike poles attract. In the case of like poles, there are two instances of like poles repelling, either two south poles or two north poles. For demonstration purposes, let's observe two north poles as our example. The circular shapes around the magnet represent the magnetic field. To the right, I'll add a second magnet with the same north pole pointing at the first magnet. Note that the field patterns are pushing against or repelling one another. This repelling phenomenon will occur whether or not two north poles or two south poles are brought together. In this example, let's first bring in a north pole. The magnetic lines of force are flowing out of the north pole. When we bring in a south pole, the lines of force are flowing into the pole. The force of attraction can be felt between the two magnets. This attraction will become stronger until the two magnets literally stick together. Placing a ferrous metal bar in a magnetic field will cause some of the magnetic vanes to realign, and the ferrous metal will become a magnet. Once you remove the magnet from the vicinity of the metal bar, the domains return to their previous state, but sometimes not right away. In an MR scanner, magnetic fields are rapidly turned on and off. Different tissues resonate with different frequencies. Let's explore how magnets work. The simplest way to magnetize a ferrous metal is to introduce the metal to a magnetic field. When this happens, some of the metal's domains will align with the field. The ferrous metal becomes a weaker version of the original magnet. Remove the magnetic field and the domains will return to their original state of random arrangement. The return to their original state may not happen at once. To produce a permanent magnet, manufacturers grind ferrous metals into powder, then fuse the powder into a solid bar or ring or other shape. When they subject the metal bar to a very strong field using an electromagnet, the electromagnet forces some of the domains into the new alignment, turning the bar into a magnet. Additionally, heating a ferrous metal bar can loosen the orientation of magnetic domains. Allowing them to cool in a magnetic field will cause some magnetism to remain in the metal. If you take a simple bar magnet and break it, two smaller magnets will form. A new north and south pole will form at the site of the break. Where there is a north pole, a south pole will exist. It's impossible for a north pole to exist without a corresponding south pole. The first magnets that existed were natural magnets called magnetite. These magnets were formed when molten iron cooled in the presence of the Earth's magnetic field. Under the right conditions, magnets are naturally formed. Whenever electricity flows through a conductive material, a magnetic field is produced around that material. Coil a wire and place a ferrous metal down the center of the coil, and the field will be strong enough that the circuit will act as a magnet. To summarize, here are some laws that all magnets follow. All magnets have two poles, one north and one south. This is known as a dipole, di meaning two. The monopole doesn't exist. Break a magnet and one half of the break will form a south pole and the other half of the break will form a north pole to complement the existing poles. Like poles will repel, unlike poles will attract. When ferrous metals enter a magnetic field, the metal becomes magnetized. Being magnetized, it will attract to a magnet, and the magnet and the ferrous metal will stick together. Whether talking about two magnets or a magnet and a piece of ferrous metal, the inverse square law applies to the force of attraction or repulsion. The force of attraction or repulsion changes as the reciprocal of the distance squared. For example, the closer two magnets are, the greater the force of attraction or repulsion will be. This will end my presentation. Thank you.